Okay, thank you very much for coming, both in the room and online, which is really exciting. So welcome to the Marine Biogeochemistry session for the MASTS conference. We're really excited about the diversity of talks that we've got, which really reflects biogeochemistry, which by definition is multidisciplinary as well. So talks are 12 minutes, and we will have some questions at the end. We will have questions in the room, but anyone online that has questions can also type in their questions and we will bring them up. So let's kick off. First up is Elena Cappelli from St Andrews with peat erosion in West Shetland.
Okay. Hi everybody, thank you for having me here and thank you for being here. This is my first MASTS meeting, so I guess introductions are in order. I am Elena, I am based at the University of St Andrews and I'm a research fellow. What I do in St Andrews is working on sediment coming from fjords, and specifically I want to understand what is the relationship between organic carbon enrichment in these fjordic sediments and their possible impact on benthic communities. Specifically, I'm working with benthic foraminifera. So this is a bit of an overview of the next 12 minutes. I will start with a brief introduction about the area of study, which is in Shetland, specifically our 6 voes on the west coast of Shetland, and I will highlight the main research questions behind my project. And then I will move on presenting the main results of the 2 studies that are part of this project. The first study aims to characterize the sediment properties in these voes, while the second part of the study is a faunal study, where I am looking at the foraminifera assemblages, trying to understand how they respond to the different environmental properties that we can see in these voes. So, about the area of study, why studying fjords and why study them in Shetland? Well, a good number of studies recently show how fjords are very effective in storing carbon. Actually, fjords have been defined as hotspots for carbon barrier and storage. So this is one of the reasons why I'm looking at fjordic systems, because we know that they can store large quantities of carbon, and by doing so they reduce the remineralization of carbon in the atmosphere, and thus they reduce the release of CO2 back into the atmosphere. But what about the benthic community living in these sediments? Are they affected by this higher concentration of organic carbon? So this is the big questions. And to answer this question, I basically have these smaller questions. So we know that we have this high organic matter and high organic carbon content, but where does it come from? Does it have a land, like a terrestrial origin, or does it have a marine origin? And about organic matter, what type of organic matter we have in this location? Is it like refractory or is it labile? And this will affect our benthic communities because, like, for example, labile organic matter is the one that is more easily uptaken by our organisms. And what about carbon? Do we have more inorganic carbon or more organic carbon, and what that means? And then the next 2 steps are, once we define our environment, how do our communities respond to these changes in the environment, and can we use these changes in the composition of our benthic communities to infer back into the properties of the environment? So to answer some of these questions, I will start by presenting the main results from the sediment characterization study. So I'm trying to define spatial distribution, source and type of organic matter and carbon in these 6 voes in West Shetland. And here you can see a map with the location of the 6 voes, and then like zoom in maps, where in this case we can see the variability of organic matter. The size of the pie charts show like how much total organic matter we have in the different voes. And what it is obvious is that total organic matter is higher closer to land. This basically suggests that most of this organic matter comes from land. If we look at the colors of these pie charts, we see that most of this organic matter is refractory, the brown color. And this again tells us that most of this organic matter most likely comes from land, specifically from the surrounding peatland, as Shetland is covered in peat. And what about carbon distribution? Once again, we see a sort of parallel distribution between organic matter and organic carbon. Organic carbon here is the green part of the pie. Again, organic carbon, as we have seen for organic matter, is higher close to land. So once again, pointing to a land source of organic carbon. And in contrast, inorganic carbon is more abundant towards like open sea conditions. So suggesting that the storage of inorganic carbon is controlled by marine processes. But what is the bigger picture? Like what happens when we combine all this data together? So on top of the organic matter measurements and the carbon measurements, I also have carbon stable isotope measurements, and I know the water depths of the 21 locations from where we collected our samples. And I put them together using principal component analysis. And what I obtain is a plot in which we can identify 4 main groups. Actually, the first thing that we can see is a clear division between the marine area and the land area. And this division is driven by the stable carbon isotopes. Higher delta 13C values identify more marine location, and lower values are indicative of terrestrial location. And then if we focus on the terrestrial location, so on this part of the graph, we see a certain variability. And this is because the range of water depths is much higher because of our data set in the terrestrial location rather compared to the marine location. So we can identify a terrestrial and deep location and a land-dominated and shallow location, whereas the marine location has a more uniform water depth, so we can't do this type of discrimination. And then we have a smaller group at the center, which is a transitional group, so it's not quite terrestrial or land-dominated like this one, but not yet open marine. So we have these 4 groups, like marine, terrestrial. Among the terrestrial, we have the deep and the shallow, and then we have these transitional environment. So this is our picture when we look at the sediment. But what happens when we look at our benthic foraminifera assemblages? We will see a similar pattern in the composition of these assemblages. Well, this is a map that shows the distribution of our species of benthic foraminifera. So I picked the benthic foraminifera in all of the 21 stations, and I found a total of 52 different species. But of these 52 different species, these 8 species pictured in this graph are the dominant ones. So they account for more than 80% of the total variability. So this is why I'm now focusing only on this one. And these 8 species are the ones represented in the pie charts. And as you can see, we do see a variety of, it changes in the composition of these assemblages. In certain cases, we have a dominant species, in other cases, we have a different dominant species, and sometimes we have higher diversity and we can't really identify a dominant species. But what does this mean? Like, does this reflect changes in the environment, or are these changes driven by something else? So to answer this question, I compiled together the sediment data I presented before and these foraminifera data. And what we see is exactly the same for clusters I was talking about before. We see again the terrestrial, the marine, and this transitional, and each one of these clusters has specific forums. So the terrestrial cluster with the deeper station is dominated by this forum called the Cappelli cover, and has also significant numbers of other 2 species. And this basically tells us that we are in high organic and high organic matter and high organic carbon settings, but also that we are in low oxygen conditions. In contrast, these other terrestrial or land-dominated, I should say, locations have a different dominant genus. In this case, all these 3 species belong to the same genus Serphyllum, which is typical of shallow waters and organic-rich waters. And once again, we can even see slight changes within the same cluster. For example, these orange stations coming from Sand Sound are dominated by these top 3, species of forams, which are typical of, or actually they can survive at low salinities, meaning that if we have river runoff, these are the species that will thrive, and this is actually our case. In contrast, this sample is dominated by these other species of Benthic margaritaceum, which is yet a shallow species, high organic, but doesn't like these changes in salinity. It's a stenoalide species. And at this location in Cliff Sound, we do have a more mixed water column. So this is actually reflected in our changes in the benthic population. And then again, marine cluster, we have Cibicidotes, which is again a species typical of this more marginal to open sea environment. And what it is interesting is that in this transitional area, which is not land dominated, but is not yet marine dominated, we cannot see an obvious dominant species. We have like the samples with the higher diversity come from this transitional area. And so what does this mean? Like, why would we want to know this? Well, because this basically tells us that we can use changes in these assemblages, like in the composition of these assemblages, to track changes in organic carbon and organic matter across the voes. And not only spatial changes, but we have the possibility to use forams which are preserved in the fossil record to also reconstruct these changes downward, so on a temporal scale. So this is quite interesting, and it is a very interesting tool to use also for time reconstructions. But the question I haven't answered yet is, okay, we have this high organic carbon and organic matter concentration, but are they affecting our forams? Like, are they bad or not? So to answer this question, I try to calculate a biological index based on the foraminifera population. And this is the very preliminary part of the study. So this is where I need to put more of the work, so powering through now. So basically, in the literature, we can, this index has been used mostly on macrofauna, and only very recently it has been used on forams. The idea behind the calculation of this index is that we can put our forams in different groups, ecological groups, based on their sensitivity to organic carbon. So we will have very sensitive species that will disappear at high concentration, and very low species, and the opposite, like opportunistic species, which will thrive at very high concentration. And then basically, once we group all our species, we can use this formula to calculate this index. And then high values will be bad conditions, because it means that then the organic carbon is so high that only opportunistic species can survive, and low values will be high quality status. But again, I haven't validated yet this index, so this is just a brief peek on what it could be, hopefully. So to sum up, based on the sediment study, we found that organic carbon and organic matter burial and storage in West Shetland is controlled by land processes. In contrast, inorganic carbon is governed by marine processes. What we could not do due to the resolution of our sampling grid was to understand also if fish farms can be a source of organic carbon. More likely they are, but we weren't just able to see that. We just need a tighter grid to actually be able to see the influence of fish farms. But it's definitely something that's interesting to keep in mind for the future. And based on the foraminifera assemblages, we do see that they reflect changes in organic matter and organic carbon, so they have great potential as proxy to reconstruct these changes both spatially and temporally, and over time. And about using forams as indexes, we do see a potential, but we still need to validate this index to make sure that it's actually a realistic tool and not just, there is no bias, let's say. So thank you very much, and if you have questions.
Okay, any questions from the floor?
Two questions. First question, in terms of having this distinction between organic carbon-rich and inorganic carbon-rich sediments, is there also a difference in trading and sand content at the same time? And does this kind of influence as well, which kind of
Yeah,
species you get?
so I don't have at the moment for the surface like grain size measurements, but just by looking at the sample when it was processing it, yes. So there is like the finer material usually is associated with more organic rich areas, and the quartz material is more like the open sea, marginal sea. Yes, there is definitely